Calibration slope can expose probabilities that look acceptable by Brier score, but are systematically too extreme. You'll fit a binomial calibration GLM and flag globally high, overconfident probabilities from its intercept and slope. I'm Professor Pi, teaching AI foundations with simple Python. Imagine a loan model that ranks risky customers well. The riskiest people still appear near the top, but its predicted chances may be too high across the board, or too dramatic at both extremes. Brier score, a metric for average squared probability error, can miss that pattern when different mistakes partly cancel out. Calibration asks a simpler question. When the model says a group has a certain risk, does reality support that risk? Statsmodels is a good fit here because it lets us model observed events and predicted probabilities directly, then inspect clear coefficients instead of building the calculation from scratch. We will start with a small held-out table of predicted risk bands and real outcomes. Then, we will measure the broad shift, check whether the probabilities are too extreme, and produce adjusted risks that better match what happened. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a compact view of predictions alongside the outcomes they were meant to describe. This snippet creates a compact out-of-sample calibration table with NumPy. The model's predicted risk levels lit in risk, while events and total summarize what actually happened in each risk band. That keeps the example visually small, but it still represents the same ingredients you would have after scoring held-out loan, churn, or diagnosis cases. NP.average computes the weighted average gap between predicted risk and observed rate. So the first signal is a global shift rather than a full calibration diagnosis. The output shows the held-out sample size and average risk gap, which tells us the probabilities are high overall. That average gap is useful, but it cannot tell us whether the model is also stretching low and high risks too far apart. This example fits the calibration model with statsmodels using SM-GLM. A good ranking score can hide whether probabilities are shifted or too extreme, so the code regresses observed binomial outcomes on logit risk. sm.addConstant adds the calibration intercept, and sm.families.binomial tells statsmodels that yCount contains event and non-event counts. The fitted cal.params are the two numbers we need: intercept for broad risk shift and slope for probability spread. The output shows both estimates, which turns a vague calibration problem into directional evidence. Those two values are informative, but they become much more useful when we translate them into a decision someone can act on. This code converts statsmodels' calibration coefficients into plain diagnostic labels. The intercept check handles the global direction. A negative intercept means observed odds are lower than the original probabilities implied around the center. The slope check handles extremeness. A slope below 1 means the original probabilities are spread too far apart for the observed outcomes. The small threshold band avoids treating tiny numerical wiggles as a real issue, which is useful when sample sizes are limited. The output names the two failure modes separately, so the next action is not just improve calibration, but correct high and overconfident risks. Before we reuse this on real model scores, we need to protect the calculation from probabilities that sit exactly at the edges. This snippet adds a small guardrail before taking logits with NumPy. Exact 0 or 1 probabilities can appear after rounding, bucketing, or very confident models, and their logits are not finite. np.clip moves edge values just inside the open interval without changing ordinary probabilities in a visible way. The 1e-6 value is a pragmatic numerical buffer. Making it larger is more conservative, but can distort extreme probabilities more, while making it smaller preserves extremes, but gives less protection. The output confirms every safe logit value is finite, which prevents a brittle calibration fit. Now that the input is safe, we can turn the diagnosis into a small, reusable recalibration pattern. This example wraps the whole calibration baseline into fit calibration. The function clips risk, builds the logit design matrix, fits SMGLM with a binomial family, and returns both the statsmodels fit and recalibrated probabilities from fit.predict. That gives you a small reusable pattern for held-out predictions before deciding whether to deploy a recalibration layer. The final MAE compares the recalibrated probabilities with observed rates across the same bins, weighted by total. The output gives a compact error summary and a concrete action, completing the path from diagnosis to a minimal recalibration step. This example shows why calibration is more than one overall error score. A negative intercept points to risks that are broadly too high, while a slope below 1 says the model is too confident at the extremes. Fit this on data the original model did not train on, because testing calibration on training data can make a weak model look trustworthy. Try changing the clipping buffer and see how it affects edge probabilities. Then, apply the same function to a true held-out prediction set and compare the original and recalibrated risks by band. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.